Hello, in this part of the training, we are going to cover natural refrigerant air conditioners. This is a very simple substitute for conventional split and window air conditioners. Let us see what we are going to cover in this training module. We're first going to understand the environmental issues related to natural refrigerants or alternate refrigerants right now. We are then going to cover the entire spectrum of refrigerants that are available for conventional cooling technologies, and we're going to try and see where natural refrigerants fit into the picture. Beyond that, we're going to get more focused on the specific natural refrigerants which can right now, today, replace the conventional refrigerants which are harming the environment and increasing the energy consumption from air conditioners. We will then look at one specific natural refrigerant which is called R290. R stands for refrigerant, and that one is also called propane. It's a natural substance that exists in many natural environments. Beyond that, we are going to look at specific applications of this technology in the form of split air conditioners and centralized ACs. So let's look at the entire spectrum of refrigerants that are available to designers and manufacturers. The first differentiation that can be made in the refrigerant food chain or the refrigerant family is fluorinated versus non-fluorinated gases. Fluorine, as we all know, is a chemical substance represented by the symbol F. And if you look at all of these refrigerants here, they all have one common element, which is fluorine. This is chlorofluorocarbons, this is hydrochlorofluorocarbons, perfluorocarbons, hydrofluoroethylenes, and hydrofluorocarbons. On this side, in the non-fluorinated category, you will see all of these substances lacking this element of fluorine. Natural refrigerants are one subset of these non-fluorinated gases. What is the primary environmental issue with conventional refrigerants which compels us to look at alternatives? The primary reason why we are trying to get away from high global warming potential gases or conventional refrigerants is the fact that all of these refrigerants have a disproportionately high impact on global warming compared to carbon dioxide. So let's first understand this term, global warming potential. As we all know, greenhouse gases come in many different varieties. All of them have a differing impact on radiative forcing, as it's called, and all of their radiative forcing or warming effects are compared to carbon dioxide, and a number has been assigned for each of these gases. For instance, if you look at the most commonly used refrigerant in India right now, for air conditioners at least, is R22, refrigerant 22, whose chemical symbol is, well, it's a hydrochlorofluorocarbon, it's a chlorodifluoromethane. Now, one molecule of that gas, when it leaks out into the atmosphere, has 1,810 times the impact of one molecule of carbon dioxide leaking into the atmosphere. Therefore, these are called super greenhouse gases, not just regular greenhouse gases. What we could first start doing to reduce the environmental and climate change impacts of air conditioners is to go away from these very high global warming potential gases and start moving to the ones that have much lower global warming potentials. For instance, one refrigerant that is now being marketed in India as a low global warming potential gas is this one called R32, which is a hydrofluorocarbon. As you can see, it's still fluorinated. It still has a relatively high global warming potential compared to carbon dioxide. Now, the reason why this is called as low global warming is because it is much lower than what is currently the median or the average kind of refrigerant that is available, which is 1/3 of what is the average in the market. However, you can see that it is much higher than the potential natural refrigerants that we could be moving to. Hence, stopping at this point does not make much environmental sense. Why don't we go to the most sustainable and low global warming potential gases available to us right away, especially since the technologies have already matured. So, to put this environmental issue in another, or understand it in another way, we have been on what's called a chemical treadmill since the birth of the air conditioning industry. If you all recollect, in the early 90s, the predominant environmental issue that the world was dealing with was the ozone layer issue. It was getting depleted because of the leakage from cooling devices of a substance called chlorofluorocarbons. They subsequently got banned when we realized the detrimental effects of these gases on the world's environmental health and the people's health. We substituted chlorofluorocarbons with a solution which solved the ozone problem to some degree, however, started leading to other environmental issues. That first step on the chemical treadmill was the transition from chlorofluorocarbons to hydrochlorofluorocarbons. Over time, even these have been people have been realizing that these gases not only not solve the ozone problem completely, they also have started creating global warming potential issues or global warming issues. Over time, these are being phased out. However, instead of phasing them out completely and moving to completely natural solutions, the conventional industry still wants the air conditioners to step down in small steps so that we can create alternate products that can still be used and still keeps a few of the players relevant and in the market. For example, one stopgap solution is hydrofluorocarbons. And as you can see, if there are opportunities to have a few more refrigerants between the completely sustainable solutions and these, the industry will try to maximize the number of refrigerants it can sell to us before it goes into this. It's kind of like what happens with iPhone versions, where the future iPhone versions might have already been designed and ready to go. However, the smaller the number of steps between one version and another in terms of features upgrade, the more the industry can extract money from the consumers. This is a similar attitude that's being adopted by the air conditioning industry. So what we would like to suggest is, we would like us to move from this current refrigerant that we are using in our air conditioners, all the way jump right to the natural refrigerant technologies. This process is called leapfrogging. It is very useful for India because India is not a saturated air conditioning market. India has right now about 41 million ACs, room ACs installed in its homes, whereas the population is close to about 1.3 billion. As you can imagine, there is a big unsaturated market for air conditioners, and if we can switch our refrigerant right away, we can make sure that the next 1 billion people who consume air conditioners do so using the most sustainable refrigerant available to us. That's why leapfrogging is most relevant for India, much more than any other country in the world right now which is dominated by an air conditioning demand. For instance, China has about 1 billion ACs already installed, and they cannot leapfrog because they are already locked into a technology which is based on hydrochlorofluorocarbons or hydrofluorocarbons. One must wonder why such a big environmental issue is not part of the mainstream environmental discourse. While you often hear about the energy consumption of ACs, the heat that they generate, we also hear about other environmental solutions related to global warming. We almost never hear about the refrigerant part of this. One of the reasons why we don't hear about this right now is because if you look at this chart here, this is a chart from a research paper by Welders in 2009, and it has subsequently been accepted by the United Nations as an authoritative analysis of the refrigerant issue in the world. It shows that since the year 2000 to up to the year 2050, what is the expected transition of refrigerants going to look like? On the y-axis, you will see the emissions in terms of the gigatons of carbon dioxide equivalent per year, And here you can see the years counting up from 2000 to 2050. As you can see, in the dark blue band, those are the chlorofluorocarbons. In the light blue band, those are hydrochlorofluorocarbons. And in the yellow or cream band, it's hydrofluorocarbons. Over time, as the Montreal Protocol, which banned chlorofluorocarbons, proceeds and it's adopted completely across the world, you will see that the chlorofluorocarbons are no longer a relevant refrigerant. We are almost at 2018 now, and you can see CFCs are no longer the dominant refrigerant. They have been replaced by hydrochlorofluorocarbons. Over time, what's going to happen is even this refrigerant is going to become less and less relevant, and they're going to be replaced under a business as usual scenario by hydrofluorocarbons. However, the sum total of the refrigerant in 2017, the amount of emissions from that are still quite small compared to what will happen if the growth of air conditioning continues unabated across the world. So one of the reasons why we never hear about this issue is because we are perhaps in our nascent phase as a planet with respect to the amount of refrigerants we need, because global warming hasn't really taken root yet. But once global temperatures rise, and that creates very pronounced hotspots in our cities, the amount of refrigerants are expected to balloon very, very quickly. And you can see by the year 2050, they become a significant amount. So let's understand this issue a little bit further. This chart here is a zoomed in version of the previous chart. Here again on the x-axis, you will see the years from 2000 to 2050. Over here, on the y-axis, this is the consumption of refrigerants, of just hydrofluorocarbon refrigerants. And what is their growth expected to be? And in terms of gigatons of CO2 equivalent per year. And as you will see, the hydrofluorocarbon market is about to go through a massive explosion. If you can look at this plume, it almost looks like a exploding gas plume. If we allow ourselves to continue down this path, the emissions from this one gas could dwarf all the other greenhouse gases, and all the other efforts that we are making to reduce global carbon emissions will be completely nullified if we allow this growth to happen. So this is the most emphatic statement that one could make about the need for natural refrigerants, or need for refrigerants that don't have fluorine in their chemical mix. This statement has been endorsed by the United Nations Framework Convention for Climate Change. This statement says that if we only focus on reducing carbon dioxide and other greenhouse gases such as methane and nitrous oxide through very, very exemplary efforts, by reducing the amount of cars we use, by reducing the amount of fertilizers we put on our fields, by reducing the amount of energy consumption through lighting, through air conditioners, all of those will pale in comparison to the exorbitant impact that this one gas will have on our collective fate as a planet. It says that this one specific gas could be responsible for 28 to 45% of the world's carbon footprint by the year 2050. So an issue which is almost non-existent in our mainstream environmental discourse will start dominating our mainstream environmental discourse by the year 2050. So instead of reacting to it when it's too late, like we have been doing in the past, and repeating the mistakes that we often make as problem solvers, let's try and avoid the problem to begin with by adopting natural refrigerants right away, especially in India, where leapfrogging is possible. Moving on, once we have agreed and have achieved some sort of consensus that natural refrigerants ought to be implemented, we can look at the options that are available to us. Natural refrigerants can be classified under three categories. They're quite distinct. The first category is hydrocarbons. These are molecules with hydrogen and carbon in them, and there are many different varieties. We'll look at them a little later. The second sub-classification is ammonia. It's not a hydrocarbon, it has nitrogen and hydrogen. And the third one is carbon dioxide. There are a few other ones that are being developed. For instance, even air is a natural refrigerant, and so is water. However, for cooling purposes of the kind that we need in our buildings through air conditioning, hydrocarbons are considered to be the best bet that we have right now, and that technology is the most mature in terms of refrigerants for air conditioning. Now let's understand the benefits of natural refrigerants before we move ahead and try to understand how they can be used as alternates. What are natural refrigerants, first of all? A natural refrigerant is a substance that occurs naturally in the biochemical processes of the earth. It does not have to be manufactured. Now you might be wondering, even though coal, for instance, is a natural substance, do we, as climate change solving communities, do we advocate the use of coal even though it's a natural substance? We do not, because coal is useful only when it is burnt. However, natural refrigerant air conditioners use hydrocarbons. For sure they are fossil fuels, but they are not used as a fuel. They're used as a captive substance. They do not actually leave the air conditioner's circuit. Yeah, so let's keep that in mind, that it's different from the conventional uses of hydrocarbons as fuels. They can be used as cooling agents to replace fluorinated gases, so that's a property of natural refrigerants. They also do not deplete the ozone layer. We do not want to regress by having gases which have no global warming effect, but then again start depleting the very fragile global ozone layer that we have on our earth. And most often they're actually more efficient than the business as usual gases such as R22, and thereby reduce the energy consumption of air conditioners as well. Why should we be using them? Besides the obvious environmental benefits, they also help India and other countries achieve the targets that they have committed to under the Montreal and the Kyoto Protocol. Both of these are very vital environmental protocols that India is party to. The Montreal Protocol is the protocol that requires us to reduce ozone depletion from India, and the Kyoto Protocol is the protocol that asks us to limit our global warming impacts. This is what is pointed out over here, and now we're going to look at the properties of R290 refrigerants through 4 dimensions. We are first going to understand the environmental benefits and implications of R290, which is the most dominant alternative refrigerant right now, at least in the case of India. The second parameter that we're going to look at is the safety. There are some safety issues that we must understand, and we must understand the implications of the design of air conditioners because of this safety issue. Because as you might have guessed, hydrocarbons are a flammable substance, but the equipment that uses them is not flammable. And we're going to try and understand this very vital nuance shortly. We will also understand the efficiency benefits, which is the reduced energy benefits of using R290 in an air conditioner compared to conventional refrigerants. And finally, we're going to look at the economic implications of using this refrigerant versus conventional refrigerants. Moving on to the environmental benefits and concerns of these gases. So first, let's understand what this chart is. This chart presents the most conventional current refrigerants used in India right at the top. The first 2 are a hydrochlorofluorocarbon. This one is called R22 or HCFC22. The second one is HFC410A. It is a fluorocarbon, a hydrofluorocarbon, not an HCFC, and is currently being sold in India as a green refrigerant. There are many ad campaigns that try to elevate its importance in our community as a environmentally friendly refrigerant. However, we must question this through facts and figures, and we're going to get into that shortly. The next refrigerant listed here is what's called a hydrofluoroolefin. This is also being portrayed as an alternative to the conventional refrigerants, and its merits are being quite exaggerated in the current media, and we're going to look at why we must be a little concerned with this refrigerant as well. Finally, at the bottom of the table here, you will see HFC32. We have encountered this refrigerant in the previous slide. This is a hydrofluorocarbon. Yes, it has a lower global warming potential than the current mainstream alternatives, but it's still quite high. And finally, the natural refrigerants. The first attribute that we can pay attention to is the ozone depletion potential. Now, the ozone depletion potential of R22 is not zero. This is the one thing that differentiates this current refrigerant from all the possible alternatives. So, of course, this has to go because the ozone issue can re-emerge if we do not, if you're not safe and we act recklessly as a community. The next attribute is the global warming potential. You can see that HCFC 22 or R22 and HFC 410A both have very high global warming potential, which immediately calls into question how this gas can ever be portrayed as a green refrigerant. Nonetheless, this misinformation is quite pervasive right now in the ad campaigns for ACs, so we must really pay attention to this number of global warming potential before classifying a refrigerant as green or suitable for an alternate cooling technology. Moving on, HFOs. Now, if you look at just these two numbers, the ozone depletion potential and global warming potential, you might think that HFOs are a great alternative to the existing fluorinated gases. However, there is one impact that is not mentioned here, which is the local pollution impacts of this technology. So there is a trade-off. We might be able to solve these global issues of ozone depletion and global warming. However, we might lead to another very difficult problem to deal with in the future, which is local air pollution. So there are recent studies that have been published in technical journals, which categorically estimate the local air pollution impacts, the fog impacts of these gases being released, especially during winter time. And we all already know the impact of these kinds of activities on the air pollution levels, the toxic air pollution levels that Delhi, Kanpur and a lot of northern Indian cities are feeling during winter. All of them will get exacerbated because of the emissions of HFOs, for instance. Therefore, this technology also is not a completely safe technology. We might be unleashing another Pandora's box of environmental problems if we go down this road. Moving on to the next one, you can see that HFC 32 or R32 solves one problem to some extent, but not completely. Hence, that also, according to us, is a suboptimal solution. Moving right to the bottom, the natural refrigerants have no ozone problem. They also do not have a global warming problem. However, R290 has one issue which we now need to zero in on and try to dissect a little bit more. It's its flammability, right? Revisiting that topic again, because it's a hydrocarbon, there is a potential for it to catch a flame. And only if we have equipment which is able to minimize the amount of leakage of this refrigerant into the spaces where people are occupying, will we be able to use this technology to replace the mainstream air conditioners. We will look a little bit more into this issue in the coming slides as to how can this gas with its flammability properties still become a safe equipment for people to use. So focusing further on this issue of the flammability of these gases, first let's understand what are the methods through which the environmental flammability and toxicity impacts are classified for an air conditioner, for a refrigerant. So on the one axis you have toxicity of the refrigerant, and on the other axis we have the flammability. As you can see, toxicity is called class A and class B, and we'd much rather be in the lower toxicity range rather than being in the higher toxicity range. And with flammability as well, we'd much rather be in the class 1, which is refrigerants which don't have a flame propagation or they're less flammable, compared to being in the class 3 range. Now, the current refrigerants that are being used in India and across the world, in air conditioners at least, are usually in this specific box. They are not toxic and they are not flammable. However, this classification hides one very important truth about these refrigerants. It's their global warming potential. if you took into account the global warming potential, they would not come across as so preferable compared to the other alternatives that we need to move to in light of the fact that we have a global warming issue going on right now. So R290, the refrigerant that we are discussing right now, is a A3 class refrigerant, which means it is not toxic, however it has high flammability. So now let's understand what are the design principles that we need to apply to our air conditioners so that these equipments are still safe for human consumption. Before we move to that technical understanding of this issue, first let's understand how living with hydrocarbons or living with substances that can light up and cause a flame or even an explosion is part of our day-to-day lives. For instance, a lot of people use fossil fuel driven vehicles on a very regular basis. A lot of these vehicles have flammable fuels, right? So for example, compressed natural gas, a very common fuel in India. Cars have these, but we don't call our cars flammable. We call the fuel flammable, but not the car, because the car has applied certain engineering principles, or the designers of cars have applied certain engineering principles which make the car safe for people to use. Similarly, liquid petroleum gas. Now this gas is what we use in our kitchens in India to cook. That fuel, of course, is flammable, which is why it is useful as a fuel. But you wouldn't call the kitchen in which a LPG cylinder is stored flammable. Again, certain design principles have been applied, certain safeguards are in place to make sure that even though the fuel can light up, and in fact does light up, which is how it provides heat, the entire equipment is still safe for human consumption and human occupation. Yeah. So another thing to keep in mind is in both these cases, we are living with large quantities of these gases in our proximity. For example, in the case of a car, you might have a few dozen liters or kilos of a flammable fuel. And the same thing with a liquefied petroleum gas cylinder, an LPG cylinder. Most homes have about 14 kgs of this gas in their proximity while they're cooking. Now, if you look at the refrigerant quantity in an air conditioner, the quantities that we are talking about are very, very small compared to these. For instance, in a typical 1 or 1.5 ton air conditioner, the amount of refrigerant does not exceed 400 grams. Hence, we must look at the flammability issue in perspective as well. We can't compare the amount of substances in a refrigerator or an air conditioner with these conventionally used fuels that are in our homes and in our vehicles all the time. So let's understand the technical implications of this flammability of R290. The thing to focus on here is this term called the lower explosive limit. Now this is a term that indicates the percentage by volume of this refrigerant that needs to be present in a occupied space. Say this room over here has a certain volume. Say the volume of this space is about 100 liters, the volume. Only if you have 2.1 liters or more of this space occupied by the gas that has leaked into the space will there be some chance of a flame catching. As long as the percentage is less than 2.1, which means even if it's 2 liters and not 2.1, this room is safe for human occupation. However, of course, being engineers that are trying to safeguard human safety first, even before we look at global warming potential, we would need to stay much lower than this value to make sure that there is absolutely no chance of an explosion happening where a natural refrigerant AC is possible, where a natural refrigerant AC is installed. All right, so let's look at the implications in terms of the sizes, in terms of the amount of refrigerant that you can have to make sure you don't violate this very cardinal limit. All right, so the equation or the mathematical relationship that helps us use that value of the lower explosive limit to arrive at a certain maximum allowable refrigerant in one AC is this equation. This equation is used by the ISO standard and the European standards to define the maximum allowable refrigerant in an AC. As you can see here, the maximum allowable charge is a function of the room area, is a function of the lower explosive limit, and is a function of the room height as well. Okay, let's take each of these parameters and understand why they are present in this equation. First of all, room area. It is quite easy to imagine that the larger the room area, the more space you have for the refrigerant to disperse, and thereby the percentage, the volumetric percentage is reduced to safe levels even if you have a leak. Yeah. So the larger the room area, of course, the amount of mass that you can have in a refrigerant in an AC in terms of the R290 content can be larger. The lower explosive limit. The higher the lower explosive limit, the safer the refrigerant is, right? So R290 would have a 2.1% and you would plug this into this equation right here. Now, why is the height of the air conditioning equipment vital? If you look at the screen over here, right, imagine if this was an air conditioner, and say at the midpoint of this screen is where the leak happened, right? So imagine the cool air is coming here and the refrigerant is in a tube behind the screen. If a leakage happened, because this gas R290 is heavier than air, it would tend to settle down in the lower reaches of this room. It will not disperse uniformly across the space. What that does is that it limits the volume available for dispersal, and hence one must account for only the part of the room below this height and not the entire room. So that's a very conservative way of designing. If you account for that accurately, you will have a safe air conditioner. When this is plugged into conventional air conditioning installations in India, we can actually derive the maximum allowable mass of R290 in an air conditioner, and we will look at that number in the next slide. When you plug in the parameters that are often seen in a room in terms of installation height, usually ACs in India are installed at a height of about 7 to 8 feet. And if you look at the room sizes that are usually available for air conditioners to be installed in, it turns out that if you use that previous equation, for a 1.5 ton air conditioner, a hydrocarbon AC, one cannot have more than 360 to 365 grams of R290 and still call it safe. If we are below it, we are safe. If we are above it, we have a chance of some amount of flammability. Therefore, this limitation is required to be followed by every natural refrigerant AC that is sold in the market, and the ones in India do follow this very, very stringently. All right, we have here summarized the implications of that one equation and the other properties of R290 into a simple summary for architects and engineers. The first implication is that the distance between the indoor and the outdoor unit cannot be more than 20 feet. Now, what does that mean? That means that the amount of tubing between the two vital parts of an AC have to be less than 20 feet. The reason for this is that even if you make the tubes as narrow as feasible in terms of engineering design, you will violate the mass requirement of 365 grams if you have a tubing that is much longer. Because the longer the tubing, the more volume you have to fill, and the more volume you have to fill to maintain the same pressure, you will have to increase the amount of mass that is present in these tubes. So one very clear constraint is this 20 feet. The second constraint is that because of the fact that there might be misuse of this of the air conditioner in spaces where you have naked flames. So for example, in a restaurant kitchen where you're trying to cool the space and there might be sources of ignition available, to be safe, an R290 AC should not be used there. In these instances, you might want to move to other refrigerants which are not flammable at all. Finally, the other two considerations that you need to keep in mind is that if you have a typical installation height of about 7 feet, which is about 2.2 meters, you need at least 113 square feet of room area if you want to have 1 ton of this air conditioner installed in that room. which means that if you, for example, have a room size of 100 square feet, this AC, if installed at 2.2 meters, will not have enough dispersal area if a leakage does take place. So one immediate implication of this is in the case of ATMs in India. Most ATMs in India have or ATM rooms rather, have an area of about 80 square feet, which means that none of these ATMs can safely use an R290 AC because there won't be enough area to disperse that gas if a leak happens and still stay within 2.1% of the lower explosive limit. Or for a 1.5 ton AC, if you want to use that, you must have at least 170 square feet of dispersal area. The other option is you install the AC at a higher height, which means you need a lot of room height to be able to use these ACs in areas less than this. Finally, because this is a refrigerant that requires a lot of careful refilling, a lot of careful emptying out. For instance, the person who is filling or emptying out this refrigerant while maintaining it cannot have a source of ignition or a flame in their hand, for example, a cigarette or a BD, etc. So this cannot be used in situations where the person who is the owner of this equipment is neglectful and does not care about safe maintenance of this AC. So we would not recommend people use this in applications where there's possibility of neglect of safety considerations. Once we've understood the safety implications, we can look at the efficiency benefits of this refrigerant compared to business as usual refrigerants. The key parameter to understand before we understand the benefits of energy efficiency is this term called coefficient of performance. This term essentially calculates the cooling output that you get in terms of kilowatts to the amount of energy that you are putting into the system. The higher the amount of cooling per unit of energy that you put into the system, the better the coefficient of performance. This is the basis of the Bureau of Energy Efficiency star rating system. Now let's look at the COP of R290 as a refrigerant compared to the conventional business as usual refrigerants. This is shown in the chart here. Let's first demystify what this chart is trying to tell us. On this axis here, you will see all the conventional refrigerants that we've already visited in the past. And here are the physical and chemical properties of this refrigerant as you go down the rows. The first one is a volumetric refrigerating effect. We will come to this a little bit later. But the one to focus on right now with respect to the efficiency is the COP, as was introduced in the previous slide. If you see the COP of R290, the one that we are studying right now, its COP is 4.28, which means per kilowatt of power that you put into the AC, you get about 4.2 kilowatt of cooling out of it. Now that is higher marginally than the current refrigerant that is being used, R22. However, that is being phased out. So what we must compare it with is actually the replacement refrigerants that are being advocated right now in media by manufacturers, etc. Those are R410A and R32. These are the currently promoted refrigerants by the mainstream industry. And as you can see, R290 is much better than both of these alternates for room ACs, significantly better in terms of coefficient of performance. So as you can see, as long as you can curb the flammability of these ACs through the design principles that we spoke of earlier, they are more efficient. And we're now going to look at another environmental or another benefit of these ACs once we understand how these ACs are efficient. So to understand this, we must keep in mind this parameter of volumetric refrigerating effect. One can imagine that the greater the refrigerating effect, which is the kilojoules of cooling that you can get per meter cube of the refrigerant, the better a refrigerant is, right? It shows that it is able to pick up a lot of heat in a very small volume, which is the main job of a refrigerant. Now, if you look at these numbers, it is quite perplexing how R290 can have a higher coefficient of performance despite having a lower volumetric refrigerating effect, right? So it's quite confounding. We will address this apparent anomaly in the next slide. To understand how a refrigerant can have a better COP despite having a lower volumetric refrigerating capacity, we must understand that the key parameter that determines the efficiency of an AC or the coefficient of performance is not just the volumetric refrigerating capacity. It also depends on the amount of refrigerant I am able to push through the compressor per stroke of the compressor, which is called the compressor displacement rate. So you can have a low volumetric refrigerating capacity in terms of per meter cube of refrigerant. But if I need to move much less refrigerant than would have otherwise been the case, then you can still have a better volumetric efficiency. And now this is possible because of the higher density of R290 compared to business as usual gases. So this paradox of having a relatively low kilowatt of cooling per meter cube of refrigerant, but yet having a high overall efficiency is depicted here. As you can see, R290 can have a low kilowatt per meter cube of refrigerating capacity. However, if it has a very high amount of refrigerant that I can move per compressor stroke, then what happens is that per unit of compressor stroke displacement, I can have a relatively acceptable kilowatt of cooling, which is what this relationship depicts. And hence R290, despite having a disadvantage in one parameter, is able to compensate for its deficiency there by having a high density which the compressor is able to harness, and hence has a good overall efficiency compared to business as usual refrigerants. The final parameter we're going to look at with respect to the overall virtues of R290 compared to other conventional refrigerants is the fact that it has a low price. It has a low price directly in terms of the material that you buy, but it also has a low impact in terms of intellectual property and this idea of the commons. These gases are universally available. They do not have large corporations that are required to manufacture these gases, and hence can be manufactured locally. So they have a lower environmental cost as well, and allows small communities to take control of their cooling, which currently is not the case because of our over dependence on large multinational corporations and their complex synthetic fluorinated gas products. Yeah, so this also is a virtue of the R290 compared to R22 and other conventional refrigerants. Once we've understood all the physical, chemical and economic attributes of R290 refrigerants, let's look at how they have been applied in day-to-day applications in India right now through looking at split ACs that use R290. It might sound a little surprising, but there are already products in the market, though they are not the predominant market shareholder in India. There are products that use only R290 in the air conditioner, and we're going to understand how they perform compared to their peers. So this chart here is a bar chart which indicates the performance of the green bar, which is the hydrocarbon air conditioner, compared to the conventional ACs available in the market. So let's focus on this set of bars here. You can see that this is the comparison for a typical split AC with 1.5 ton capacity, and this is for a 3-star air conditioner. This can be considered to be the most conventional kind of AC in India, would be a 3-star 1.5 ton split AC. This is the power the AC consumes when it's running, and as you can see, a typical 1.5 ton split AC of 3-star attribute would consume about 1.8 kilowatts of power. The same cooling performance by a hydrocarbon AC would require only 1.4 odd kilowatts. What this does is that every AC that is replaced by a hydrocarbon AC generates approximately 350 megawatts, this is the reduced amount of energy that has to be generated at the power plant, and this amount of energy can in a way be released into the grid so that it's available to less privileged communities. Now this number of 350 watts, let's understand what other services can it provide to the communities that don't have access to adequate amount of energy. 350 watts of power can actually power about 7 ceiling fans. So in a way, if we think about one home, a 2-3 bedroom apartment having 2 such ACs, and if they are replaced by a hydrocarbon air conditioner, this would release approximately 700 megawatts into the grid, which can then power close to about 10 odd ACs, 10 to 12 odd ceiling fans in a neighboring slum or a neighboring chawl, etc. So imagine one apartment can lead to provision of thermal comfort to about 12 other homes if it switches to natural refrigerant ACs. The reason why we have a low energy consumption or low power consumption of these ACs compared to business as usual is because of their much higher coefficient of performance. As you can see, for a typical 1.5 ton split AC of 3 stars, it usually has a coefficient of performance close to about 3. Yeah. However, a Godrej Eon AC, which is one of the manifestations of this hydrocarbon technology, it has a COP of about 3.7, which is approximately 20% better than the average AC available in the market. To further understand the economic benefits of having a more efficient AC, we conducted a life cycle costing study which illuminates this point that not only are these ACs environmentally beneficial, they also have very direct economic benefits. This is a life cycle cost of a 3-star split AC in India, which runs for approximately 1,000 hours a year. Yeah, that's close to about 3 hours a day for the full year, or slightly longer periods of day for a smaller number of months, which is during the summers. Yeah, so that's a typical usage pattern, about 1,000 hours per year. A split AC, a 3-star split AC in India, which does not have natural refrigerants, will require over 10 years approximately 1.6 lakh rupees to run, depending on, of course, which city you're in, etc. But this is an average cost to run the AC over 10 years. And its starting cost is about 28,000 rupees. Now, a alternate refrigerant technology unit, such as the Godrej Eon AC, which has R290 as a refrigerant, might cost initially a little bit more. You can see that this costs approximately 9,000 rupees more for a 1.5 ton AC. However, over its life, you consume much less energy and hence you spend less as well. On a life cycle basis, the cheaper AC is actually the Godrej Eon AC. Therefore, there is no real disparity between economic and environmental considerations as long as we adopt a long-term view on things. This is exemplified by this chart. Switching of one of these ACs to a Godrej Aeon ACs enables these kinds of benefits if one home were to adopt it. For example, if one home which has 3 of these ACs were to replace them by Godrej Aeon ACs, they would be able to power 36 ceiling fans. They would save about 10,000 rupees annually if 3 ACs were being replaced. 120 light bulbs could be lit in other people's homes, and it would be the equivalent of 3 cars being taken off the road in terms of reduced pollution and global warming impacts. Therefore, this is a win-win-win technology environmentally and ecologically. Now, those were the room ACs, split ACs. What can be done to switch out and replace the large chiller-based air conditioning systems that are quite prevalent in India's commercial buildings? So let's look at centralized air conditioning systems which can use R290. Now, you might be wondering that since we had those very strong restrictions on the amount of refrigerant that can be enclosed in one air conditioner and still keep it safe for human occupation, how do we address the cooling needs for large buildings which will obviously need a proportionately larger amount of refrigerant in their circuit? The way these systems are able to achieve them is by having a part of the unit outside the building, which is how chillers operate. So chillers are systems which have a cooling system which cools a circuit of water, and it is the water that is circulated through the entire building. Therefore, the safety rules can be different because there are no humans in the part where the refrigerant is enclosed. It's only tubes of water, and the safety considerations for water are very different from those of human occupation. So these systems are able to have 2 cooling loops. One is the refrigerant cooling the water, and then the cooled water going into the building. And in this way they can have systems as large as 200-300 tons. So here's an example of a building in England, the Westminster Abbey Church House. It has a cooling system which has a capacity of about 150 tons of cooling or 600 kilowatts of cooling, and it uses R290 and it uses chiller loops. So it's a completely safe, large-scale chiller system which has a very low global warming potential. And if you look at the performance parameters of the R290 system and the previous hydrofluorocarbon-based system, you can see the environmental benefits. The environmental benefits emerge from the higher COP of R290 compared to the conventional system, and that is approximately 21.2% better. This is a direct translation. This has a direct translation in terms of money saved per year and also the reduced global warming impact. Yeah, and this is a picture of that system, and as you can see, the cooling system is placed outside the building, and it's only the cooled water that's allowed to go into the building, and hence it's safe as well. If you have further questions, please do not hesitate to get in touch with us on our email addresses or through our portal fairconditioning.org. Thank you.